All right. So the plan for today, I'll talk about reaction time 2, which is an implicit bias study once again. I'm also going to talk a tiny bit more about the implicit association test. So there were some things that last time that I wanted to touch upon just in a tiny bit more detail related to order effects in the implicit association test. So that's not actually stated here. I'm going to begin class talking a little bit more about the implicit association test, and then in particular order effects. Then we'll talk about reaction time 2. Then we'll talk about correlational designs. I had planned to have 2 in-class activities today. One of them I would prefer you to actually complete by yourself. The other one you can do either by yourself or in a group. So there's 2 activities today. I don't think I'll be talking for that long. And then you'll use the rest of the class for in-class activities or for working on coding your group project 1 or running participants or talking about your introduction sections that you'll be writing here in the near future. So starting talking about the implicit association test for race, we talked about it a lot last time, and I just want to remind you that on the left here, these are 2 different screenshots kind of stuck together. On the left here is what's typically known as the compatible condition, compatible with presumed stereotypes related to white and Black Americans. So this would be considered the compatible condition because assuming that racism exists, it tends to assume, bad things with Black Americans, the stereotype, and good things with white Americans would be the stereotype. So this is compatible with the presumed stereotype in Western countries, or at least America. This is the incompatible condition of the implicit association test for race because it's inconsistent with the presumed stereotype regarding Black and white individuals in America, or at least Western countries. Okay, so yeah, and remembering the task that people perform, you would see something that would appear in the middle of the screen. It would either be a white face or black face, and your job is to categorize it either to the left or to the right by pressing the E or I buttons on your keyboard, or on some of the trials, you would see a word like happiness, which would be a good word, or misery or something like that. That would be a bad word. And your job, whether it's the compatible condition or the incompatible condition, is basically to categorize each thing that appears in the middle of the screen as belonging to the left or belonging to the right. And in general, we found that it's been found numerous times in numerous studies, we talked about some last time, that reaction times tend to be slower for the incompatible condition compared to the compatible condition. I'll point out that for our lab 4, we actually didn't replicate that. That's the first time in about 5 or 6 years of my doing the implicit association test that a class has not shown statistically significant implicit bias on the implicit association test. But that's literally the first time that's ever happened. Usually it's a pretty strong effect. And overall, with all the research that's occurred, it's a pretty strong effect. Implicit bias in the IAT for race, so slower reaction time for the incompatible condition compared to the compatible condition. So I'm showing this stuff again, these order effects, because this was one of the factors, the 2 factors for the implicit association test that we did lab 4. One of them was compatibility. That was a within subject factor. So half the trials that you saw were compatible trials, and then the other half of the trials you saw were incompatible trials. That was everyone that took lab 4. The within subject factor was compatibility. Everyone experienced both levels of that factor. The other factor was the order with which you went through the different levels. So half the participants saw the compatible condition first, and the other half of the participants saw the incompatible condition first. And so here are data from an implicit association test. So these are not race. These are not the data from the implicit association test for race. These are the data for the implicit association for flowers and insects. So it's basically the exact same thing, except instead of black and white faces, you have flowers and insects, but a similar task and a similar set of findings, where people show that for the incompatible condition, they are slower compared to the compatible condition for flowers and for insects. But there was these order effects that I did talk about a little bit last time. And you can see, like, once again, I want to remind you, just focus in on the left side of these graphs. The stuff on the right, it basically says the same thing, but you can get the important concept just from focusing in on the left side of these graphs. This is really all that matters for these. And the two really crucial bars that you want to focus in on are the black bar, which is, it says non-compatible, but that means the same thing as incompatible. And the white bar, which is the compatible condition. The dependent variable is latency, which just means reaction time. And the IAT effect, or the degree of implicit bias that one shows, is measured by the difference in reaction times between these two conditions. And so, once again, this is the flowers insects IAT. So this is not the race IAT. This is looking at implicit bias regarding flowers and insects. And you can see that there was an IAT effect. So I guess one other thing to say is you can see here that people in this condition right here, they did the non-compatible condition first, and then they did the compatible condition second. Down here, it's just the opposite. You can see the white bar here, they did the compatible condition first, and then they did the non-compatible or the incompatible condition second. So the order of the bars from left to right, these are just the practice trials right here. This is the non-compatible condition first, compatible second. Here's the compatible condition first, the non-compatible second. In both situations, they're looking for the difference in reaction times between those two conditions. And that is the magnitude of that difference in reaction times between those two conditions is the implicit association test effect. And there was a 145 millisecond difference here. So when non-compatible, the incompatible condition was first, the amount of IAT effect was 145 milliseconds. However, when the non-compatible condition was second, the IAT effect was 234 milliseconds. That is the difference between the black and the white bars was a difference of 234 milliseconds. So in other words, the IAT effect is stronger in this situation here than it is here. And that was shown statistically in this paper by the compatibility by order interaction. This represents a difference. This 145 represents a difference. This 234 represents a difference as well. If you compare the magnitude of this difference to the magnitude of this difference, this difference is significantly bigger than this difference. So if you kind of think about it, we're looking to see, are these differences significantly different from each other? That's why it's an interaction. We're looking at the difference of the differences. And this one was bigger. So this is a significant order effect. And the explanation for this is right here. Basically something along the lines of this is the picture for race. I don't have pictures of the flowers and insects one, but basically for the first half of the trials, you get used to every time you see a white face, you press E for left. And every time you see a black face, you press I for right. But then halfway through the experiment, this changes. And then now black face is on the left and white face is on the right. So you have the memory of something, you have the memory of doing one thing earlier. And then when that changes halfway through the experiment, that memory of what you did earlier kind of interferes and makes it a little harder. In other words, when you get right here, your brain is still kind of used to every time you see a black face, your brain is used to saying I for right. But halfway through the experiment, that changes, and then the answer would be you would start pressing E for left. I'll shut this door. And this is kind of the explanation for why there's kind of two things going on right here. There probably is actually implicit bias, and which explains why people are slower for the incompatible condition right here. But there's also this idea that what you did in the first half of the experiment kind of leaves a memory, it leaves a residue. And then when things change, when those labels change side, that causes some interference, which makes you slower. So there's kind of two things going on. There's the actual implicit bias, and then there's the order effect, which occur as well. Once again, this is for the insects and flowers example from the Greenwald et al. 1998 paper. This is the paper that was cited 13,000 times, so a very influential paper. This, I don't believe I showed you last time, but this one's pretty fascinating, actually, to me at least. So this is the same idea here, except instead of this being the implicit association test for flowers and insects, this is the implicit association test for race, that is white and black faces. And what you see, so let's see right here, this is compatible condition first and then the incompatible condition second. And then here is the incompatible condition first and the compatible condition second. They call these things slightly different labels, which is kind of annoying, but the black is still incompatible condition and the white is still the compatible condition here. And once again, we're looking at the magnitude of the difference between the incompatible and compatible trials, and that is our implicit association test effect. And you can see here for when compatible is first, incompatible is second, the effect is 213 milliseconds. Here, where the incompatible condition is first and the compatible condition is second, there's a difference of 201 milliseconds. So this is in the expected direction. That is, it is expected that the IAT effect will generally be stronger when the incompatible test is second. The incompatible condition is second. So that's in the right direction because there's a difference of 213 milliseconds here and a difference of 201 milliseconds here. However, in this study, the compatibility by order interaction was not significant. So this is interesting. This is not something they focused in on in the study, probably because they don't understand why this happened. But once again, for the flowers and insects, there was a significant interaction. There was evidence of order effects. This difference, this IAT effect, was significantly bigger than this IAT effect right here for flowers and insects. For the race, for white and black faces IAT, that difference was not significant. So 201 was not significantly quicker than 213. So the trends were there, but the difference did not reach significance, which is interesting. It's a very similar experiment as the flower insects one, except it was with black and white faces instead of flowers and insects. And yet, and although they did find the main effect of compatibility, that is, people were slower in the compatible conditions, they did not show the interaction, which is surprising. And so, yeah, I think I showed you this last time. We didn't show the significant main effect of compatibility in our lab, and we also didn't show the order effect. It might be because our sample size was small. There might be other reasons why we didn't show the main effect of compatibility. And this is kind of repeating some of the statistical things I just said about the Greenwald study. But part of their issue is they didn't, for their race IET in the Greenwald study, they did not show the compatibility by order interaction. It's not exactly clear why. It might be the case that there, for some reason, which is currently unknown, which is what I believe to be the case, there are no order effects for racial bias. There is order effects for bias related to the flowers and insects for whatever reason. But for racial bias, at least based on the results of Greenwald 1998, there is no statistical evidence that there's actually an order effect here, which, as a cognitive psychologist, that's actually an interesting thing because it suggests that the mental mechanisms which are going on for these two types of bias, flowers and insects, is one type of bias, and then their racial bias is a different one. They only found the order effects for one thing. They didn't find the order effects for the other, which suggests that mentally there's different phenomena which are going on in people's head, which is something that should probably be investigated more. Part of the issue, though, with their study is that they had a small sample size for their racial bias study of only 26. So their interaction for the racial bias study didn't reach significance, but it might be because it was underpowered. So you would need a larger study to see if it would become significant. And last time when I was talking, I said I hadn't found one yet, but I've done some research, and I have found one right here. This is another highly cited study by Nosik, I believe is the way this individual's name is pronounced. So I found this since last time, and I read the study since last class, and I think it's quite relevant here. Because basically, I think I've discovered a phenomenon that no one in this literature has really explained yet. And that's what I'm going to talk to you about right now. And I'm doing this because in the spirit of, this is a science class where you're learning to become scientists, basically. And basically, I'm kind of sharing with you what I think is my motivation for potentially doing a follow-up study on this exact topic, because there seems to be a question on this which is unanswered related to order effects in racial IAT studies compared to other IAT studies which don't involve race. So here is a large study from 2005 where the sample sizes were bigger. And they did a whole bunch of different IAT studies. So they had a black-white one. So this is the one, you know, the racial bias one right here. Then they did a IAT study with old and young individuals. So presumably there are stereotypes about old and young individuals as well. I'd imagine young people are generally presumed to be the good. That would be the stereotype. Young, good, old, bad would be my guess. There's also a gender science stereotype experiment. My guess here, going with my knowledge of stereotypes, is basically in this study, men are presumed to be more sciencey and women are presumed to be less sciencey. That would be the stereotype. That would probably be the compatible condition here. There's also an Asian white IAT here, which I would imagine, given that this was a study that was done in the West, in America, or England, I'm actually not for sure which. Presumably the compatible condition white would be paired with good and Asian would be paired with bad. I don't actually know what this dark light is. This might just be dark versus light skin IAT. And then average effect is basically just taking all of the other IATs and combining them into a single score. For our purposes, really, we just need to focus in on these top 4 different IATs. And what I was interested in is, do they show order effects in these studies? And if you can look, one of the factors in this study is order. For half the participants in each of these 4 IATs, they saw the compatible condition, they call it the compatible block first. And then the other half of the people, they saw the incompatible block first. And then what they calculated was that same difference score. Though I think they standardized this because they have decimals. So this is not reaction times per se, but it basically, you can kind of think of as what you're seeing here as reaction times. The bigger, but it's reaction times that are different, the amount of difference between the incompatible and compatible conditions. So in other words, the bigger these numbers here, the bigger the IAT effect, the bigger the difference in reaction times between the incompatible and compatible differences, though it appears that they standardize it. So these aren't actually in seconds units, it's in some standardized unit instead. But what's really interesting here is that if you look at the strength of the IAT effect and the racial one, there's basically no difference right here. The 45 and 0.46, they're basically showing that the IAT effect is the same for the racial one, whether they're showing the compatible condition first or the incompatible condition first, which is exactly what they showed in that 1998 study, but which they kind of didn't really even try and talk about. They didn't try and explain. This study replicated. This study didn't really try and explain this either. What's interesting about this is the only one out of all 4 of these right here, or actually all 5 of these, only one out of these 5 that did not show a difference in the strength of the IAT effect, depending on whether the compatible condition was first or the incompatible condition was first. If you look here for the old-young stereotype, the IAT effect was stronger when the compatible condition was first and relatively smaller, 0.44 is smaller than 0.53. So there's a difference here in the predicted direction that the IAT effect is stronger when the compatible condition is first and the incompatible condition is second. Same thing over here. In fact, it's quite strong for the gender stereotype one, where there's a very big IAT effect, 0.56 for the compatible first situation, and then a relatively smaller IAT effect for the incompatible first situation. And that's basically the same pattern for all of these IATs with the exception of the black-white one. And this is a phenomenon. Now I've been doing a little research and I talked to several people this week, and this is a phenomenon that like no one writes about. This phenomenon has happened multiple times, at least in these 2 studies, and in neither of these 2 studies do they ever talk about it. They like pretend that this isn't happening. And as a cognitive psychologist, that seems to be like there's something theoretically interesting going on there. You're seeing order effects for all of these IATs, but for this racial one right here, there's consistently now 2 different studies have not shown order effects, which means mentally there's something unique which is going on here, which is not going on for the other IAT studies. So that's really all I have to say about that. So I will talk about reaction time 2 now, which is the study that you read for today. So this is another, basically by the time we're done with this week, we'll have talked about 3 different measures of implicit bias. IAT, the priming study of reaction time 1, where people had to decide whether they were looking at a gun or a tool, and they were primed with either a black or white face. That was reaction time 1. This study is the shoot versus don't shoot paradigm, where people are shown pictures, and I think I have the pictures, yeah, right here. They're probably not going to be they're kind of small, but if you read the article, then you saw these same pictures. This appears to be a black individual holding something which is not a gun. This is a white individual holding something which is not a gun. I think that's a white individual holding something which is not a gun, a black individual holding something which is not a gun, a white individual holding a gun, and a black individual holding a gun. And your job as a participant in this study was to make a decision whether to shoot or not shoot the individual on the screen. Obviously, if the person's holding a gun, you would make the decision to shoot. If the participant is not holding the gun, then you make a decision to not shoot. The primary dependent variable in this study was reaction time, although they are interested in like study 2. I think they are interested in error rates. So the main findings here, which are very consistent with, I think, what your expectations would be, given what we've talked about in implicit biases for race already earlier this week. White participants were the main studies in all of the experiments, all of the studies in this paper. White individuals were the primary participants, except for study 4, where they included black participants as well. And so for all of the studies, the white participants were faster to shoot a black armed individual than a white armed individual, which is consistent with the pattern of implicit bias against black people, where you would, if they're armed, you would make a decision to shoot them. It's easier for you to make that decision to shoot a black person who's armed than a white person who's armed. Also, which is really interesting, and this is a consistent finding in this paper, the white people were faster to decide to not shoot an unarmed white person compared to an unarmed black person. So in both these situations, if the person's unarmed, you should not shoot. But when that person was white in this study, they made the decision to not shoot that white person faster than they made the decision to not shoot a black individual. So both of these are the primary findings, I would argue, and they're both present in all of the studies in this paper, are quite consistent with this idea of implicit bias that we've been talking about all week. Probably one of the most interesting aspects of this study, though, is that black participants showed the same pattern of reaction time as white participants. And I think I have those data right here. Yes. So here are the white participants looking at armed targets. So the correct response here would be to shoot. And so when white people are seeing a white armed person, it takes them 590 milliseconds to decide to shoot. But then if they're seeing a black individual who's armed, they're 12 milliseconds on average quicker. So it's not a huge difference, but it was statistically reliable, at least in this study, a difference of 12 milliseconds where they were faster to shoot armed black individuals than armed white individuals. When they're unarmed, this is a question for me. Yes, I do think that is a possibility. Ahmed asked, do you think that there can be problems with the study as the gun in the black person's hand is clearly shown while the one for the white person is close to his body? Yes, I think that is a possibility. And I don't know enough about their stimuli to know if the stimuli that I showed you earlier, Ahmed, that might just be, yeah, and then Abigail responded, I think that they had everybody in all of the poses. So yeah, if there was a good study, which I haven't seen all the stimuli, if it was a good study, then they would make it so that the stimuli, every time you saw a person holding the gun outside of their body who was black, you would also have a white person who is doing the same pose. I don't know that for a fact. So that is a good criticism, and I'd have to look at the details of the methods to see if that's something that they explicitly said that they were something that they were trying to take into consideration. Like, it's a cool question, and it's a potential group project 2 study idea. You could actually look at this type of thing, and you could manipulate the poses of the participants to see if the specific poses of the participants actually does have an influence on the reaction times. So I don't know your answer for sure, Ahmed, but I think that is a possibility. I think what you're saying is a possibility. Okay, so continuing on, the white people who, when they're unarmed targets, so here the correct answer would be not shoot. And when it's a white person who's unarmed, 652 milliseconds. When it's a black person who's unarmed, they're relatively slower to make that decision to not shoot. So it's harder for them to say not shoot when it's an unarmed black person compared to when it's an unarmed white person. And then what's interesting, though, is that for the black participants in this study, they showed basically the exact same pattern of results. So they were quicker to shoot other black individuals by 11 milliseconds compared to armed white individuals. And they were also quicker to not shoot unarmed white individuals compared to unarmed black individuals. So this is obviously a little bit of a controversial finding, but it's could be applicable to obviously modern. In fact, the in-class discussion activity or the in-class question is basically I kind of interested in you kind of connecting some of these ideas on implicit bias to some of the events that have been going on in America, recently, past few years. But I feel like this year has obviously been a particularly important year regarding those events, police shootings. Yes, so controversial findings. There possibly are alternative interpretations. Maybe the black and white individuals had different poses, and the poses of the black individuals showed the gun more. That's a possibility. I don't know if that is the correct answer or not. Oh yeah, and then one other thing. This is another reason I'm bringing this up is because this last point right here. Study 3 was the only one that included an explicit measure of racial bias. The reason I bring this up is because last class I talked about the distinction between implicit and explicit bias. Explicit bias is basically when you can say verbally, I hold a bias against so-and-so group. Implicit bias, you might say, I do not hold the bias. But if you look at the subtleties of the behavior, in these cases, it's measured in reaction time in these three different paradigms that we've talked about, then you might see evidence of bias, even if the participant will not explicitly say that they have bias. And what's interesting about what's kind of interesting but also problematic is that basically implicit tasks, like the three that I've talked about this week, are kind of notoriously bad at predicting people's explicit racism. So just if you actually say, yeah, I'm explicitly racist against this group, or I hold biases against this group, that does not necessarily predict that you're going to show a shooter bias. I think it says it right here. Yeah, explicit racial bias, which they call prejudice composite, did not correlate with reaction times in this study. Bias is illustrated by the difference in reaction time between black or white people that you're seeing on the screen, depending on whether they're armed or not. And I think I have that shown right here, this graph. So this is a correlation matrix. Each of these things in here, starting here, all of these numbers in here, these are R values. They're correlation coefficients, which is something you should learn about in stats and methods. And basically, the further away this value is from 0, whether on the positive or negative side, the stronger the correlation. If it's got these stars here, that means that it passed a statistical threshold where you would consider it statistically significant. And if you look at the prejudice composite and shooter bias, although that was in the predicted direction, the more prejudice you claim to be, the more bias you serve in sort of your reaction times. That is, being faster to shoot a black individual relative to a white individual, the difference in reaction times. So it's in the expected direction, but it did not, reach the statistical threshold where it be considered significant. However, there were two things that were significant, probably the most relevant of which is cultural stereotypes. So if you are an individual that tends to believe that a black culture is more violent than white culture, those individuals showed more evidence of shooter bias compared to those that do not hold that stereotype. So there were some things that correlated with shooter bias. The other one was contact, which is very difficult to explain. And it went in the complete opposite direction of what I remember for a different class before I had read this paper, I had made the prediction that I think individuals that have had more contact with people of the opposite race will show less racism and less bias. So you would think that the more contact you had, for instance, with a black individual, if you are a white person, the less bias you would show, the less implicit bias you would have against those individuals. But they found just the opposite. They found a positive correlation where the more contact you reported in a self-report questionnaire with individuals who are Black, the stronger your shooter bias. And they were not able to explain that. That's just something they were not able to explain. And I don't know how to explain it either. The cultural stereotypes one, that one makes a lot of sense to me. This one doesn't make any sense to me. I just don't know how to explain it. But so it's food for thought. It's some interesting findings. And I'm sure there will be research which is building on this in the future. Okay, so here, actually, I'm going to skip over this now. This is the first in-class activity. I would not suggest you starting this now because I'm going to talk about some things, and then there's another in-class activity which you need to stay tuned for. So you're going to have two in-class activities today. This is the first one, and I'll come back to this, or it's also in the slides that are posted. Just a little bit more now. I want to talk about correlational designs. I just showed you that correlation matrix, and each of those values in that correlation matrix was an R value, a correlation coefficient. And I'm going to briefly review to you, I believe this is review, what an R value is. And then I'm actually going to show you the formulas, and then I'm going to show you how to calculate one. And then your second in-class assignment today is using Excel to calculate a correlation coefficient for a very simple data set. This is just kind of, if you're rusty on what a correlation is, this is just meant to kind of get your brain activated, remembering this concept of correlation. So this definition, probably everyone's pretty confident with still. Correlation, the linear relationship between two variables. One variable is usually called X, the other variable is usually called Y. Correlations can either be positive or negative. Looking at this thing, this is an example of a positive correlation. This right here has a negative sign in front of it, so that would be an example of a negative correlation. I'll show you some examples of positive and negative correlations. Correlations can also differ in their strength. So if you have a correlation coefficient of 0, that's as weak as you can possibly get. And then strong correlations are just far away from 0, either on the negative side or on the positive side. So a correlation coefficient of -1 is a strong negative correlation, and a correlation coefficient of +1 is a strong positive correlation. But the strength of -1 and +1, they're the same. Just the direction is the only thing that differs between a correlation coefficient of -1 and a correlation coefficient of +1. So yeah, here's an example of a correlation, a simple one at that. Where on the X variable is the amount of money that your family makes. I guess this would be annual income. And then a student who's a member of that family, their average grade on some class or on some type of a test. And this would be, let's see if you guys can remember, would this be considered a positive or negative correlation? Anyone tell me? I have a chat. Thank you, Ahmed. It is a positive correlation. And positive correlations go up and to the right, up and towards the right, whereas negative correlations go down and to the right. So I think I have one of each here. So here is an example of a positive correlation right here. The X value here is temperature, so how hot it is outside. And the Y-axis is amount of beer, a cold beverage, sold. So as the temperature outside gets hotter, the more beer is purchased and more beer is sold by companies. That is a positive correlation. As the value of this variable increases, the value of this variable increases as well. A positive correlation, it's going up and to the right. Here is an example of a negative correlation. Temperature is still the X on the X-axis, but here it's the amount of coffee, which is usually a hot beverage, the amount of coffee sold or the amount of coffee purchased. As the temperature increases, the amount of coffee purchased or the amount of coffee sold decreases. This is a negative correlation because as this value increases, this value decreases. As one goes up, the other goes down. It is going down and to the right. Positive go up and to the right, negative go down and to the right. Any questions or comments on the difference between positive and negative correlations? All right, moving on. So here are some different correlations. Again, this would be a negative correlation with a correlation coefficient of -1. I know it's negative because it's going down to the right. I know it has a very strong correlation because each of these dots falls exactly on the same line. They're forming a perfect line. The closer each dot is in a scatter plot to this line of best fit, the stronger the correlation coefficient. So this is as strong as you can possibly get. This is definitely a correlation coefficient of -1. It is a perfect correlation. All right, here, this is a positive correlation coefficient, and it's we know it's weaker than +1, because if you draw that line of best fit right here, it'd be something right there. Some of the dots are above the line of best fit, some of the dots are below the line of best fit, and it's definitely the case that not all of the dots are falling directly onto the line of best fit. So positive correlation with a moderate strength. Here, this is like a correlation coefficient of 0. If you were to draw, there basically is there's no positive direction or negative direction. If you were to draw a line of best fit, it would basically be a flat line. You know, it'd be like, it's like dead. It's a correlation coefficient of 0. There's no positive relationship here. There's no negative relationship here. There's just no correlation here at all. And then finally, here's a negative correlation. It's subtle. There's definitely a negative correlation, though. If you look, the dots are kind of going down and to the right, but it's a weak negative correlation coefficient, not a strong one, because if you draw the line of best fit, you can see that the average distance of each dot is somewhat far away from the middle, from the line of best fit. So the further away the average distance of each dot is from the line of best fit, the weaker the correlation coefficient is. The closer that correlation coefficient will be to 0. So that should be a review of strength and direction of correlations. This stuff may or may not be reviewed. Not all statistics classes will actually calculate correlation coefficients. I think it's really helpful for understanding how they work. And so I'm going to have us do this one time, where we're going to, at least one time actually, where we calculate correlation coefficients. So here is how you calculate an R value. So you're taking the sum of something. The thing that you're taking the sum of are Z's and Y's multiplied by each other. And I'll show you exactly what these are. So these are Z-scores, which is something you should have learned about in stats. Basically, everyone should be familiar a little bit with what a Z-score is. You calculate a Z-score for each X value in a data set. You calculate a Z-score for each Y value in a data set. For each participant, they're going to have one X value and one Y value. You're going to transform that X and Y value to its corresponding Z-score, and you're going to multiply those two numbers together. You'll do that for one participant, and you'll do it for the next, and the next. You do it for each of the participants, and then you'll sum up all of those numbers. So you'll multiply these two numbers for participant, and then the next participant, and the next participant. You'll do that several times, and then at the end of doing those multiplications for each person, you add up those numbers together, and then you divide by the amount of participants minus 1. That's how to calculate R. Of course, there's this Z thing right here, which you did learn about in stats, but I imagine everyone's a little bit rusty with how to calculate Z values. So this here's Z for the X values is a given X value. So I'm a participant. I have a score for the X variable. And that's what that X represents right here. It's a given X value minus the M sub X, which is the mean, the average of all of the X values. You take the difference between those two, and then you divide by the standard deviation of X. So that's how you get that ZX. Obviously for ZY, it's the exact same formula, except it's a Y there, M sub Y there, and the standard deviation of S sub Y's right here. So I'm going to show you, so for the second part of your in-class assignment today, you need to calculate R for this data set in Excel. The Excel file is already available for you on Blackboard. There's 2 different turn-ins these are in the in-class discussion activities folder on Blackboard. And there's already an Excel file for you there. And I already show you how to do this one with Excel formulas. And so I'll show it to you here in this lecture, though you already have the correct answer here. You'll need to calculate R using the correct formulas for this data set right here. So I think I have, hopefully I have this up already. No, I don't, so I'll have to get it. Okay. So this is the one that you guys are going to do. You're going to need to insert Excel formulas here. You're going to need to insert Excel formulas here. Oh, I didn't erase these. So really all you're going to need to do is insert the Excel formulas here. And then these are actually going to be very easy for you because I left the correct answers in there, it looks like, which I'm bummed about, but whatever. Really, you'll have to just calculate these Z values right there. This is how I did it for the first data set. So here's the data set right here, 5, 3, 3, 1, 2, 4. And go back to the data set. 5, 3, 3, 1, 2, 4. So this is data set 1. I'm going to show you how to calculate the R values for that, or the R value for that. So first off, there's a shortcut in Excel where you can just calculate the R value using a shortcut called Correl. And then you highlight the X's, and then you put a comma, and then you highlight all the Y values, and then you press enter, and that gives you the right answer. And you can see that I got the same right answer right here. This is like the longhand method. This is like the cheating or the shorthand method where you can just get the answer instantly. I want to show you how to actually use the formula to calculate R. So here is the average of the X's. So it says A2 through A11, but there's nothing in A8, 9, 10, 11, so it ignores those. So really, you get the same answer if you said A2 through A7. So this is the average of the X values right here. This is the average of the Y values right here. This is the sample standard deviations. I'm not sure if you know how to do this in Excel. You can calculate the sample standard deviation of a data set using the shortcut. This is sample standard deviation of the X values right here, A2 through A11. These are the X values. And then here's the standard deviation of the Y values using that same formula, the sample standard deviation of the B column right here. That gives you the standard deviation of the Y's. So looking back at our formulas, what I've just shown you is a lot of the stuff. I showed you the mean of the X's. I showed you the X's, which are the data set themselves. The X and the Y's are the data themselves. And then the standard deviation, I showed you the standard deviation of the X's and the standard deviations of the Y's. And so we can calculate the Z-scores now because we know all of this information. So the way you do that, here's an example of a formula. A2, that is an X value, minus H4, which is the mean of the X's. So an X value of 5 minus the mean of the X's, which is 3, 5 minus 3, which is 2, and then divided by H6, which is the standard deviation right here. So that X value minus this mean divided by the standard deviation, that's what this is right here, and you get this value right here, 1.41421, etc. Please note where my dollar signs are, because this will save you time. You can use the drag down method or copy and paste if you put the dollar signs where I do, and then you'll do the same thing for the Y values. But B2, that's a Y value, minus I4, that's the mean of the Y's, divided by I6, that's the standard deviation of the Y's. That gives you the Z-scores for all of those Y's. Here, K2 times L2, this is where we're going now to this formula right here. Once we've calculated all of these Z formulas, all these Z-scores, we then have to use those Z-scores to calculate R. The way we do that is we take the Z-score that we calculated for X for a person and the Z-score that we calculated for Y for that person, multiply those together. And that's exactly what this is. K2 times L2 is this Z-score in K2 times this Z-score in L2, and that's the product right there. This one corresponds to the 2 Z-scores for this participant. This person's the 2 Z-scores for this participant. These 2 Z-scores for this participant, so on and so forth. We multiply those 2 Z-scores together for each participant, and we get these different values right here. And then, right here, this is the easiest part. You just sum all of these numbers right here. Just sum them together. And then And that's the reason we're summing them together, is because once we've made all the products, we have 6 of them, you just add them together. You take the sum. And then finally, we divide by n minus 1 in this r, for the r right here. And that's because n13, which is this thing, that's the numerator of that fraction, divided by f11 minus 1. So f11 is the sample size minus 1. Sample size minus 1. We're dividing by that. The numerator divided by the sample size minus 1. And that gives you our R value. And you are going to have to do the same thing. Though really all you're going to have to do is calculate the z-scores, because I forgot to erase the correct answers for these. At least I think I did. Yeah, those are correct. So that is it for today for stuff I'm going to talk about. And now I'm going to let you guys do some stuff. So once again, I've already inputted the data into that other tab on the Excel, which is on Blackboard. You're going to calculate R here. And that's talked about here. Use Excel formulas to calculate R for the second data set on the previous slide. Looking at Blackboard, let's see if we have it up already. Yep, okay. Looking at Blackboard, the discussion activities. There's the in-class activity on racial bias. I would prefer you do this one by yourselves, though if you do it as a group, I will still count it. But I'm guessing that your guys' opinions, and it asks for opinions, are not going to be the same. So I think this will make more sense. It'll be more beneficial if you actually do this one by yourself. And then the other one you'll turn in here, calculating R in Excel. So you're turning in a Microsoft Word document here, turning in a Microsoft Excel document here. Go to it. I will be here for the rest of class if you need help. Once you get done with these, use any remaining time to prepare for group project 1 things. And I will see you guys lab Friday.